to my lecture today. Before I get started today, I've already edited the deadline for assignment 8 and the final practical assignment in line with the syllabus. I just wanted to, you can check that. Okay, the deadlines are already updated. Okay. Okay, so the final announcement this week, before the end of this week, probably on Saturday, you actually going to receive final practice questions. So you can check the canvas for final practice questions. And just like what I did in the midterm 1 and midterm 2, I'm also going to walk you through the final practice questions. Okay, I want to welcome you to my class today. Today, we basically want to focus on analysis of categorical data. Now, before I go into this, I want to have a recap. I told you the other time that the kind of method or statistical method we use depends on the nature of data, particularly the nature of the response variable and the nature of the predator. Now, I could remember when we started, if you want to if you're trying to characterize a relationship between variables, and if the nature of the response is continuous, okay, you're basically going to fit linear regression. You're going to fit linear regression depending on whether other assumptions hold. Because I told you the other time, the specification of statistical model is followed with assumptions. I remember when you are fitting linear regression model, one of the conditions is that the response variable that we call the outcome variable should be continuous. The predator could be categorical, could be quantitative, there's no problem. Now, when we get to the analysis of variance, before we can actually use analysis of variance, the response variable also need to be continuous, just like what we have in the linear regression. But you know what? It is compulsory that the predator has to be categorical for the analysis of variance. Categorical in the sense that, you know, what you do in analysis of variance is to compare groups, right? The levels will basically represent groups. So which means you are only comparing response at different levels of the categorical predator. That is for the analysis of variance. Just like what you have in the linear regression, the response variable for analysis of variance has to be continuous. Why the predator has to be categorical. But you know what? We also have situation whereby in addition to the categorical predator, we can also have a quantitative predator. But in that kind of situation, the analysis of variance will no longer be called analysis of variance, but it will be called analysis of covariance. Now from there, we move to a situation where the response variable is categorical. When the response variable is categorical, we can no longer use linear regression. We cannot use analysis of variance, but we can use logistic regression model. And I told you the logistic regression model is basically we need to transform the response variable, the logic transform of the response variable. The logic transform of the response variable is what we call the log of odd. That is what we use for situation where the response variable is categorical. But do you know what I'm presenting to you today? What if in a situation where the response variable is categorical, the predator is also categorical, the two of them are categorical. What are we going to do? Therefore, we have a special statistical model we can fit situation where the variables involved are categorical, whether the response and the predator. And that is the reason why we call the title Analysis of Categorical Data. Now, in the outline, how do we model effect of categorical predator on the categorical response? I'm going to give you this example now. I remember on Monday, I gave you an example from the criminal justice system where the court will consider some aggravating factor before they could sentence a convicted or a suspect that is guilty before the court. If you want to look at the role, if you want to look at the effect of gender on the probability that the suspect will reoffend, when you talk about reoffend, that's categorical. It's either a suspect commit a crime again or it does not commit a crime. That's categorical response. If you now want to look at the role played by gender, male or female, that is another categorical predator. How can I look at the effect of categorical predator on the categorical response? I want to look at the effect of gender on the probability that a convicted suspect will commit a crime again. In that kind of situation, you're going to use analysis of categorical data. But you know what, today I want to go away from criminal justice system. This time around, I want to come back to medicine. I want to use an example today from medicine. And this has to do with the cervical cancer and the age at first pregnancy. Now, the data actually come from a case control study where we want to examine the potential relationship between the age of first pregnancy and cervical cancer. What is the role played by early pregnancy on the risk of getting cervical cancer? The two variables are categorical because the age that we want to talk about now, we want to consider age 25 or less and age more than 25. That's categorical. And that was why I said in this study, we will be comparing the proportion of women who had their first pregnancy at or before the age of 25. Okay, because researchers suspected that an early age at first pregnancy leads to increased risks of developing cervical cancer. That is being hypothetical. That is what we want to investigate. We want to investigate that. Now, because of that, I'm going to give you the response. I want you to take a look at the predator right here. Has two levels. Age at first pregnancy, that is age less than 25 or equal to 25. And age at first pregnancy, age greater than 25, it means this is categorical. You partition the age into two categories. Let's look at the disease status as well, which is the response, right? Disease status is the response, right? It's categorical. It's either somebody developed It's either a pregnant woman develop the cancer or not. It's also categorical. That's what you see here. And this is called 2 by 2. Why do I call it 2 by 2? Because we got 2 levels of predator, we got 2 levels of response. Take a look at that. The analysis of categorical data is always presented in a table. I'm going to say that again. Analysis of categorical, when you're talking about categorical variable where the response and the predator are categorical, we're always going to have a cross tabulation like this. Now I'm giving you an example of 2 by 2. You could have situation where it is 3 by 2 or 3 by 5. The dimension, the numbers of row and the column may not be the same at times, depending on the levels of the response and on the levels of predator. But the one I'm presenting to you now is 2 by 2, 2 levels. Now, what is the meaning of this? 245 is the number of pregnant women who have their age. Who have their pregnancy at the age of 25 or less that we use in the study. 245 of them. And those who have their pregnancy at the age more than 25, they are 121. The total number of women used in this study is 366 women, pregnant women, participated in this survey. What is the meaning of 42? 42. Oh, somebody want to say something about that? Oh, okay. Good job. Now, when you look at 42, you're talking about the number of of women that have a pregnant at the age less or equal to 25 that develop the cancer, cervical cancer, is 42. What is the totality of those who develop cancer? 49. Totality of those who develop cancer, 49. 42 from those who have pregnancy early, and 7 from those who do not have pregnancy early. And when you look at 203, that is those who have their pregnancy early and they are healthy. That's control. They didn't develop cancer. And 114 as well from those who have pregnancy after the age of 25 that are also healthy. Now, this result is basically from survey. But let me tell you this. Before now, you know what you normally use? In the lower course in statistics before this class, I know what you're going to use is test of difference of proportions. Who have heard about this before? You've done this previously in a lower statistic course before you come, which is one of the prerequisites to this class. Okay, I know what you're going to do. You want to compare the proportions of those who actually develop the cancer in the 2 categories. That is what you've done previously. But that is not what we want to do today. What we want to do today, we basically want to use the idea of a special way of analyzing our categorical variable, which you're going to see now. Now, the question is, we have a research question. Every research starts with a research question. What do we want to answer? Is there an association between cervical cancer status and whether or not a woman had a first pregnancy at or before the age of 25? That is a research question. What is the meaning of association? Association means relationship. Is there a relationship between them? I'm going to start from a mathematical way. When I say there is no association, you know what that means? They are independent. No association, no relationship means they are independent. They don't have any connection. And you know what? I'm going to go probabilistically now. In probability, If you look at the probability of A given B, that's a conditional probability for event A to occur. Event B must have occurred in a situation where the conditional probability equal to marginal, then the events A and B are independent. Now here, the probability of A here is not depending on anything. This is not depending on anything, but this is depending on B. If they are equal, then they are independent. If the conditional probability equal the marginal probability, then the A and B are said to be independent. Why am I starting from mathematical angle? I'm starting from mathematical angle because four of us want to see if there is no relationship. Then after that, we will now go statistical and see whether the result is significant. The difference between mathematics and statistics, when you want to conduct, if you want to conduct a significant test, you go statistical. There could be different. There could be mathematical difference. A mathematical difference may not suggest a statistical difference. But you know what I want to start with? I, for of us, want to start with a mathematical difference. Now, what is the question? We want to see the probability. The other time that I said the probability of A given B. Give me 1 second. Now, the probability of A given B, now in relation, to what we're doing, I said the probability of A given B equal to probability of A, which means A and B are independent. In this one now, our A is age less or equal to 25. That is the early pregnancy. Now, early pregnancy, depending on what? Cancer status. If it is equal to the probability of age less or equal to 25, then it means the age less or equal to 25 does not depend on cancer status. Because of that, we're going to say the two variables are independent. And this is the interpretation here. Knowing something about the disease status, okay, does not tell us anything about the presence of the risk factor having their first pregnancy at or before age 25. Now, this is what we're going to do. We need to first find what is the probability of age less or equal to 25 from the table. I want everyone to focus the board now. It's going to be so easy. If you don't understand your ask me question, you know what I want to do first? I want to find the probability of marginal. What do I mean by marginal? I want to find what is the probability that a woman has a pregnancy at the age less or equal to 25. That is what I want to find first. Check from the table. How many women have a pregnancy at the age less or equal to 25 is 245. Divided by what is the totality of women, 366. Look at what I found. That is the probability of age less or equal to 25. Is there anyone who doesn't understand how I find that probability? Is there anyone who doesn't know how I compute that probability of age less or equal to 25 to be equal to that? Is there anyone here? Ask question. You are good, right? Okay, which means if you multiply that by 100, 66.94% of women sampled actually have their first pregnancy or are before the age of 25. This is a marginal probability. Now, the next thing we want to find now is the conditional probability. The conditional probability, we're going to have two. The first one, we want to find what is the probability of age or equal to 25 given you are given the cervical cancer. We're also going to find what is the probability of age less or equal to 25 given headache control. Oh my God, how do I get 42 over 47? 42 over 47 is actually right here. Okay, the age at first pregnancy, there are 42 of them that got a cervical cancer divided by the totality of those who have the cancer in general. That is a conditional. I will do the same for control. For the control, it's going to be 203 divided by 317. Now take a look at this. We only condition under which they're going to be independent. Do you know the only condition? The marginal probability must be the same as the conditional. Are they the same? Check. Is it 0.6694 the same as this and this? Are they the same? No. Since they are not the same, then they are not independent. You know the meaning of they are not independent? They are not independent means it depends. Too negative, not. You know what we just find out here? This is mathematical way to figure that out. But this mathematical way is not sufficient. It's necessary, but it's not sufficient. Because what this guy is telling me now, relationship exists, right? Mathematically, the relationship exists because they are not independent. They are not independent because the marginal probability is not the same. Okay, it's not the same as the conditional probability. They are not independent, but I need a statistical test to invest to see whether the relationship is significant. Right now, you know what the mathematics is telling me? Relationship exists, but we don't know whether it is significant or not. Then we now need to go statistical now. But this is the first step. Okay, now going statistical, this is what we're going to do. We have the observed 42, 7, 203, 114. They are the observed values. Okay, we need to find the expected values for each of the cells. 42, 7, 203, 114 are the observed values. I'm going to write that observed. They are observed values. We need expected value for each cell. We need expected value. And if you want to find the expected value for each cell, you know what you're going to do. We're going to assume independence. Okay? Now, take a look at this now. I'm trying to call for the 2A, B, C, D. Okay? We want to find the expected for each of that. What are we going to do to find the expected? We're actually going to equate. We're going to equate the probability of the risk to the probability of the risk given disease, which means we're going to say they are independent. That is the assumption. Assumption to figure out the expected. Now, when you see C1 divided by N is the probability of having pregnancy at the age less or equal to 25, right? When you see the probability of risk given disease, where you're going to see A divided by R1, this is just talking about the conditional. So you know what we're going to do? We're going to equate this to this. We're going to equate them. What are we assuming? We are assuming independence. Now when we assume that, we equate that. We got that. From there, we can get each of the cell. Now, let me tell you what we're going to do if you want to get each of the cell. I'm going to show you to the table. I'm going to go back to the table now because we want to use a chi-squared. Okay, if I want to use a chi-squared, we have observed. We need to find the expected. Then we're going to use this formula to get a chi-squared. But let me take you there. I'm going to show you now what you're going to do. Okay, I want everyone to pay attention now. I want to find the expected for 42. You know what I'm going to do to get the expected for 42? I need the row total, 49, multiplied by the column total, divided by the grand total. That is what I'm doing here. Look at that. If I want to get the expected, for those of you online, if I want to get the expected for 42, I'm going to use, what is the row total for 42? 49, multiply. What is the column total for 42? 245, divided by the 366. That's what you have here. Now, my expected for 42 is 32.80. Look at that. The expected for 42 is 32.80. I'm going to get the expected for 7. I'm going to get the expected for each of this. If I want to get the expected for 7, it's going to be, what is the row total? 49 multiplied by, what is the column total? 121 divided by 366. That's what I'm doing here. And the expected is 16.20. So I'm going to get expected for each of the observed value in the cell. Is there anyone who doesn't understand how to get the expected for each of that? Is there anyone? Any clarification? Row total for that, multiply by its column total divided by the grand total. That's what you're going to do. Because I have 4 cells, 1, 2, 3, 4, then I'm going to have 4 expected. Take a look at that. Now, these are the expected now. Now, I can now write them like this. What am I trying to say? That is the expected for the observed. 42 is the observed. Expected is 32.80. The expected for 7 is 16.20. The expected for 203 is 212.20, and the expected for 114 is 104.80. I think I just walk you through how I computed that. What am I going to do? Because I want to use a chi-squared, because we use chi-squared test in the analysis of categorical variable, and you know the meaning of chi-square. Chi-square is going to tell us it measures discrepancy between observed and the expected. I'm going to say that again. Chi-squared measures, okay, discrepancy, okay, between observed and expected. Okay, now what we're going to do now, we have observed, right? We have expected. Okay, what I'm going to do now, I'm just basically going to write them out. Look at that. I want to use the formula because the chi-square is going to be observed minus expected all squared divided by expected. Okay, when I do that, then I'm going to add it across. Look at what I'm doing here. The first one there, observed is 42. Minus its expected is 32.8. I square that, then we divide by the expected, then we add it to the next one. Look at that. And at the end of the day, my calculated chi-square, because the test statistic here is chi-square, I got 9.011. Is there anyone who need clarification on how I got the 9.011? Is there anyone? You guys are good, right? With the 9.011, right? Okay. Now, the next thing you're basically going to do, we need to compute the p-value. Of course, you know we use p-value to take a decision, right? This is the code right here. Now, in the code, you're going to write p-chi-square because we're using chi-square, right? P-chi-square, then q equal to the value that you got from the chi-square, 9.001, comma, the degree of freedom equal to 1. How do I come out with the degree of freedom 1? Because I have 2 by 2. The numbers of row minus 1, the numbers of column minus 1, then I multiply. What is 2 minus 1? 1, right? Another 2 minus 1, 1, right? 1 times 1, 1, right? The degree of freedom is going to be 1. So that was why I put 1. At the end of the day, look at the p-value that I calculated. Now, how can we take a decision with the p-value now? We got a 0.00, approximately 0.003. Now, when you compare the p-value, which is 0.05, what will happen? It is less, right? You know, what is the null hypothesis? The null hypothesis in this case is trying to tell us there is no relationship, okay, between the age at 4th pregnancy and the risk of getting the cervical cancer. Alternative is trying to say there is. What will happen now, because the p-value is less than 0.05, then it means you got a strong evidence to suggest that age at 4th pregnancy and cervical cancer status are not independent. You know the meaning of not independent? Not independent means they depend. Because 2 negative, not independent means they depend. It means there's a relationship. It means there's a linkage. It means there's a higher risk of getting the cervical cancer when somebody have the pregnancy at the age less or equal to 25. That is what it means. And because of that, I'm going to say, in particular, we found that the proportion of women having their first pregnancy at or before the age of 25 was higher among women with cervical cancer than those without. That is what we just find out, because the p-value is less than 0.05, and we're going to fail to reject the we're going to reject the non-hypothesis, and rejecting the non-hypothesis is trying to tell us there is a relationship between them. Because if I say not independent means there is a linkage, there is a relationship. Does that make sense to everyone with the way I analyze this? This is how we use chi-square to analyze categorical variable. I'm going to quickly walk you through another example. Example 2. This time around, this is a situation where we have the dimension, the numbers of rows and the numbers of columns is not the same here. We're talking about response to treatment and histological type of Hopkins disease. We basically want to see whether what determines patient response to treatment depends on the type of disease. That is what we want to see. Okay? I told you the other time, it is not all patients who gain from medical intervention. But this research number says example 2 is now, we're trying to see the response to treatment by patient, does it depend on the type of disease? That is what we want to do here. Now, 538 patients diagnosed with some form of Hopkins disease was taken on the histological type, like nodular sclerosis, or the means of cellularity, the lymphocyte, the predominance, or the leukocyte depletion was recorded, along with the outcome from the standard treatment, which was recorded as being non-partial or complete remission. What do I mean by remission? Remission is talking about disappearance of a symptom. It could reoccur. You get what I mean? Okay, now the research question here is there an association between the type of Hopkins disease and the response to treatment? What are we trying to say? Does the response to treatment by patient, does it depend on the type of disease? Now let's take a look at it. Oh my God, take a look at this table now. These are categorical variables. In this situation, the type of disease has 4 levels. Look at that, 4 levels. Then the response to treatment has 3 levels. Now in this situation, now we got 4 by 3. The one we did the other time was 2 by 2, 2 levels, right? But right now we got 4 levels against 3 levels. Look at that. Okay. Now, if you take a look at what I have now, 44, 10, 18, 12, 18, 74, 58, 54, 154, 12, 16, 68, they are observed values. Okay? Now, what are we going to do now? We need to first investigate mathematically. You remember what we did the other time? We want to find the probability of positive. You know what I mean by positive remission? The positive remission is a disappearance of the symptoms. That is what we want, right? Is that what we want? None is the patient is not responding at all to treatment. That's what we call none. Partial means, okay, it's responding slowly, but positive, that's what we want, right? Now we want to find the probability of positive. Now, if I want to find the probability of positive, what is the total of total positive that I have? It's 314 of the patient. They're actually positive out of 538, and that is why you see the probability of positive to be that. Now, what is the next thing? I need a conditional probability, right? 4. It's going to be 4, because that will depend on the type of disease. Okay? What is the probability of positive given LD? Okay? The probability of positive given LD is going to be 18. Look at that, divided by 72. That's why you see 18 divided by 72. What is the probability of positive given LP, MC, and S? You're going to have 4 of them. Now take a look at that. Are they independent? They are not independent. Why? They are not independent because of the fact that the marginal probability is not the same as this. That is a mathematical way. The only condition under which they're going to be independent is when the marginal is the same as that. But I told you the other time, and that was why I said, notice the conditional probability are not equal to the unconditional. The unconditional is the first one, the marginal, the probability of positive, right? Now, this is a mathematical way. What this is telling me now is that relationship exists. But this is not enough because the relationship that exists, we don't know whether it is significant. What we can call a relationship is when it is significant. So this is the first step. I'm going to show you a plot now to indicate the response to treatment that we call a Psych Plots of the results. You can see the one in blue. You can see looking at the type of disease. You're basically going to see people respond more in AP, right? AP and NS, they are over 70%. If you look at that, look at AP. AP, okay? Don't forget the positive is blue, right? People responded more in AP to AP and the NS. That is what that graph is trying to show us. But you know what? I want to go by chi-square again. I want to find the expected, just like what we did the other time. Look at what I'm doing now. For 44, I want to find the expected. The expected is going to be the row total 72 multiplied by 126 divided by the grand total. That is what you see that I'm doing there. You're going to find the expected for each of the cell. For every observed, you're basically going to have the corresponding expected, which is what we've done. Okay, now I find that, look at that. I've succeeded in finding that. You can check that. You can check how that each of that is computed. For instance, if I want to get, how do I get 48.45? How do I get this guy here? 48.45, okay, it's going to be the row total 266 multiplied by the column total 98 divided by 538. That is how we got that, you know. Now, after getting the observed and the expected, then you can go to chi-square. You can find your chi-square. The chi-square is basically going to be the observed minus expected or squared divided by the expected. Then you're going to add them up. Then you're going to get your chi-square. Now the chi-square now calculated is 75.89. Of course, you know the code now. If you want to write the code for p-value, the code for p-value is going to be p chi-sq. For that one now, let me just, it's going to be p chi-sq q equal to 75.89. Then the degree of freedom. Now, if you want to decide on the degree of freedom, you know you have 4 level by 3, right? You're gonna do 4 minus 1 times 3 minus 1. And this is gonna be 3 times 2, 6. The degree of freedom equal to 6. Okay? That was why you saw the degree of freedom equal to 6. Then when you do that, you're gonna have a p-value that will be very, very small. And when the p-value is small, what happens? What do you have in the non-hypothesis? The non-hypothesis is trying to tell you there is no relationship between response to treatment and the type of Hopkins disease. But why the alternative is going to say there is a relationship. But look at the p-value now. When the p-value is very, very small compared to the level of significance, it means you're basically going to reject the non-hypothesis. Rejecting the non-hypothesis, what does that tell you? It's trying to say there is a relationship between response to treatment by patient and the type of disease. And you know what? Even the plot here has already shown us that relationship exists. Look at that. That some patient responded more to treatment for AP and NS. Look at that. And that was why I said clearly we can see that AP and NS respond most favorably to treatment with over 70%. Look at that. That's all you can see here. Over 70%. So what is the takeaway from this research now? The takeaway from this research is that the response to treatment of patients depends on the type of disease. That is a takeaway. Okay? You know, you may also want to carry out a research where you may want to see whether the response to treatment depends on gender. You may also want to see whether female respond more to treatment than male, or male respond more to treatment than female. There's a lot of research that we can conduct. Okay? There's a lot of, for those of you, in marketing, let me just add this, in marketing, where you actually trying to measure the satisfaction of your customers, you may want to say, what is the relationship between gender and the level of satisfaction? You want to see whether male prefer your product compared to female, or female prefer your product compared to male. You're basically going to use the analysis of categorical variable. The fact remains, it's not as if I told you from day one. It's not as if our models are failing us. Our models are not failing us. But probably we are the one that we're not doing the right thing. I'm going to say that again. Our models are not failing us, but we are the one that we're not doing the right thing. What is the right thing? The right thing is using an appropriate statistical model. And when we use a statistical model, every statistical model has assumptions. In fact, I used to say this. Assumptions lead to limitations. That is my belief. If you really want to know whether your model is doing a great job, then you need to investigate conditions. You want to see whether the assumption hold. The moment assumptions do not hold, and you use that model for policy formulation, then we're going to regret our decision at the end of the day. We've seen a lot of leaders who actually surrounded themselves with advisors who listen to data scientists or statisticians that some of them that don't really care about whether assumptions are violated or not in their model. So we got to make sure, if we really want to take a decision that we are not going to regret, if we want to improve on the quality of life when we are conducting research, then we need to follow the procedure to the letter. We need to see whether assumptions that underline the use of a particular method hold. And that was why I told you the other time, a model is as good as assumption putting into a model. I'm going to say that again. A model has assumptions putting into a model. What makes a model to be great is when the assumptions are not violated. Because if you actually take a decision using a model, you know what I'm going to ask you as a statistician, I want to see where you investigate the assumptions of the model. I'm going to ask you a lot of questions about assumptions. If any of the assumptions are violated, we cannot rely on the recommendation from such research. So we care about assumption in laws. We don't just use statistical model. We actually cherish a lot the assumption. We care about the assumptions. Okay, this is where I'm actually going to stop today. You know, we are in the preparation for the final exam. Final exam has a lot of weight. Exam, just like the same way a lesson has consequence, exam also has consequence. But you know what? You are preparing for final now. Today I'm going to send a message, check the announcement section, the coverage, the area of coverage for the final. Okay, go ahead. I think I put that in the, that's a very good question. Let me just check my syllabus. I put a date on the syllabus, which is the one approved by the university. Give me 1 second. I'm going to check that right away. Yeah, somebody in the class asked about the date. Okay, authoritatively, I'm going to say, let me see whether this is for 2022. Yeah, May 11, Wednesday, May 11, between 8 and 10 a.m. That is the date of the final exam. It's in the syllabus. 8 to 10 a.m. It's going to be 2 hours. It's going to be on Wednesday, May 11. Have I answered your question now? Have I answered your question? Okay. Is there anyone who need clarification before I go today or who want to ask question? Yeah, make sure you stay safe and have a very beautiful day.